Hey folks, welcome to the first lecture for Advanced Linear Algebra, which is Math 3211 at Mount Allison University. In these videos, we're going to be going over the course notes that are posted on the course website and just sort of highlighting any particular points I think are particularly important or trying to clarify things that are maybe not so clear when just written out in text. Okay, so the way these course notes are going to work is every week will be approximately 3 or 4 lectures, and they all sort of have the same sort of structure here. So the first page of the course notes is always just this sort of title page where we talk about what we're going to be learning this week, where you can find some extra readings in the textbook, and what textbook problems you should be working through this week. So these textbook problems are not going to be graded, but they're just for your own benefit. These are sort of the same types of problems that you'll see on assignments and midterms as we go through the course, and they're sort of roughly organized by difficulty here, okay, depending on whether they're, I don't know, really easy, medium, hard, or absolutely awful. Is indicated over by the stars on the left there. All right, so let's get to actual course material. What's this course about? Well, the idea is in the previous course, so introductory linear algebra, you learned how to do all sorts of things, basically things on lists of numbers, right? Remember in that course, a vector was a list of numbers, and you learned how to do all sorts of things with those. You learned how to solve systems of linear equations, which you could think of sort of as equations involving vectors. And sometimes when you wanted to sort of transform a vector in some way, you would multiply it by a matrix, and we learned more generally how to multiply two matrices together. And then we saw that matrices have all sorts of useful properties as well. We learned about the rank of a matrix, which remember is this sort of notion of how non-degenerate a matrix is, right? A matrix has full rank if and only if it's invertible. I mean, on that note, we learned how to compute the inverse of a matrix, which was sort of the matrix that undid the original matrix, right? If the matrix A transformed vectors V in one particular way, then A inverse brought AV back to where it started. It brought back to V. In other words, A times A inverse was the identity matrix, the matrix that does nothing. We learned how to compute the transpose of a matrix, right? Remember, this is that funky operation where you take the matrix and you flip it along its main diagonal, so the rows become columns and vice versa. Okay, we learned about this connection that we've already sort of alluded to a little bit between linear transformations and matrices. There's this one-to-one correspondence between linear transformations and matrices. Every matrix is a linear transformation, and vice versa. Every linear transformation on Rn can be represented via a matrix called its standard matrix. And we learned how to compute that in the previous course. We also learned about the determinant of a matrix. So remember, determinant, this is this thing that has a big, long, hideous, ugly formula, but, all it represents, it's the signed volume of, how much the linear transformation expands space. So if you think about a matrix as a linear transformation, and then you ask the question, well, what does it do to the unit square or unit cube or unit hypercube when I apply this matrix to it, right? Depending on the dimension, if you're in 2 dimensions square, if you're in 3 dimensions cube, and so on. Okay, and when you apply the matrix, well, it blows it up or shrinks it down, but in general, like it transforms it into a parallelogram if you're 2-dimensional, or a parallelepiped if you're 3-dimensional, or hyperparallelepiped if you're higher dimensional. And the determinant is just, well, what's the signed volume of that parallelogram, hyperparallelepiped, or whatever. Okay, and we talked about that again more in the previous course. And then sort of the last thing that you typically do in an introductory linear algebra course is you compute eigenvalues and eigenvectors of a matrix. And remember, eigenvalues and eigenvectors, the idea behind the eigenvectors is they're vectors that are not rotated at all by the linear transformation. They just get stretched or shrunk, but their direction remains unchanged. Well, it might flip if the eigenvalue is negative, but they stay along the same line. Okay, and the eigenvalue corresponding to the eigenvector, it's just the amount by which that vector got stretched by the matrix or linear transformation. Okay, so if you have a particular vector that when you multiply it by a matrix, it gets stretched by a factor of 2, well, then it has an eigenvalue of 2, and that vector is an eigenvector. All right, so those were all things that we learned how to do in the previous linear algebra course. And the important thing to note about most of these operations, about most of these things, is that you could do them using only 2 very basic operations. You could compute these things using only addition of vectors and scalar multiplication. For example, if you look back at solutions of linear systems, rank of a matrix, and inverse of a matrix, we computed all of those by doing something called Gaussian elimination. And what operations did you do in Gaussian elimination? Well, you could swap 2 rows of a matrix, you can multiply a row of a matrix by a scalar, or you could add one row, a multiple of one row to another row. All of those operations, they only require you to know how to multiply by a scalar and add vectors. Okay. Similarly, product of 2 matrices, well, if you break it down, really you're just adding multiples of columns of a matrix to each other. Okay, so even matrix multiplication, same thing. You just need to know how to multiply by scalars and add vectors to each other. Okay, and that's going to be sort of a recurring theme. Well, that was a recurring theme through introductory linear algebra. And the idea behind this course is to take that observation and see how far we can push it, because there are lots of other settings where you can add things and multiply by scalars. So if you ever have that sort of structure, if you have some sort of setting where you can multiply by scalars and add things, then you can do all of these linear algebra tricks that we already know how to do. You can use all of these algorithms to compute things in these settings. So for example, in the previous linear algebra course, we always worked with vectors whose entries were real numbers, right? Vectors whose entries were real numbers. But in this course, we're going to look at vectors whose entries are complex numbers, right? Okay, so if you haven't seen complex numbers, don't worry, we'll talk about a little bit before I'll expect you to use them. Also, you can work with vectors whose entries come from finite fields. Now, probably most people taking this class haven't seen finite fields yet, unless you've already taken modern algebra. But a finite field, like sort of the standard example, is these things, where you have the set of numbers 0, 1, 2, up to p minus 1, where p's got to be some prime number for this to work. This is called a finite field, and what you do is in this set, you do addition and multiplication mod p. And what that means is just the addition and multiplication, they cycle around whenever you hit p. So for example, if I do, say, 2 plus p minus 1, well then, okay, I get p plus 1, except there is no p plus 1 in this set. You have to cycle around. You go p minus 1, okay, and then 1 bigger is cycles around to 0, and 1 bigger again is up to 1. So in this set, 2 plus p minus 1 is actually equal to 1, okay, because we're working mod p. And similarly for multiplication, if you do 2 times p minus 1, well, that's 2p minus 2, except there is no 2p minus 2. You have to sort of imagine counting from p minus 1 up to 2p minus 2 until you finally hit it as you cycle around every time you hit p. Okay, so it turns out that is an example of a set of sort of numbers that you can use in linear algebra. Okay, so you can do all of our linear algebra stuff with vectors whose entries come from this set, and you do arithmetic in that weird mod p way. You can do linear algebra like that, and everything still works out. Okay, so we're going to talk about that type of stuff. Another, maybe even more exotic example is that you can do linear algebra on sets where the vectors don't actually even look like vectors at all. In other words, they're not lists of numbers. So for example, the set of real valued functions. Okay, you can do those two operations that I talked about on real valued functions, right? You can add functions, which is analogous to adding vectors, and you can multiply a function by a scalar, which is analogous to, well, multiplying by a scalar. You can multiply vectors by scalars, you can multiply functions by scalars. So in this set, real valued functions, you have those two operations I talked about, so you can do linear algebra on it. Okay, it's an example of what we're going to call a vector space, which is basically a place where you can do linear algebra. Right? So that's the type of thing that we're going to look at in this course, or at least the first half of this course anyway. We're going to be taking all the things that we learned in the first linear algebra course and just generalizing them and seeing that, hey, we can use all of those same techniques on many other objects as well, not just lists of real numbers. All right, so let's get started with the actual math here. Let's start getting into details. So our first sort of real mathematical slide here contains our first definition, and it looks like an absolute beast, and it is, but fortunately it's the worst definition we're going to see in this entire course. So let's get it out of the way. All right, and what this is, so it's a vector space, but the idea is this is a place where we can do linear algebra. Okay, so this is the basis for the entire first half of this course. A vector space, it's a place where you can do linear algebra. So what is it? Well, basically, it's a place where you can do vector addition and you can do scalar multiplication, and they behave sort of like we expect those operations to behave. Okay, so what is it? Well, so V, this is what we're going to be calling a vector space. And then we say, okay, let F be a field. So all this means a field is just a set of numbers, basically. It's a set of things that we think of as numbers. Okay, so the real numbers, for example, that's a field. Complex numbers, that's a field. Okay, and similarly, that other weird set, the ZP, this finite field from the previous slide, that's a field. Okay, that's a finite field. All right, but for the purposes of this course, don't worry about this too much. Every time you see this funky little double F here, yeah, it's a field, but you're not going to lose too much if you think of it as just, you know, set of real numbers or set of complex numbers. We're going to be working with complex numbers a fair bit in this course, so keep that in the back of your mind. Every time you see F, you can just do a sort of a mental replacement of R or C, if you like. All right, and then what we do is we say, well, on this set V here, it's got to have two operations defined on. So these operations we've been talking about, addition and scalar multiplication. And just to give some notation to them, addition we just denote in the usual way that we denote addition, and scalar multiplication, again, we just denote it as, concatenation, just like we usually denote multiplication in that way. All right, and so we can't just have these operations defined arbitrarily though. Addition and scalar multiplication, they've got to have certain properties for the set to actually be a vector space. All right, and what properties do they have to have? Well, let's go through those now. Okay, so before we get into these, there are 10 properties here, but they're sort of grouped naturally here. The first 5 properties, these are going to concern a vector addition, and then the next 5 properties, these concern scalar multiplication. Okay, so let's go through what sort of properties does vector addition have to satisfy here. Okay, and the first property here is very natural. In a sense, it's the most important one. If you take any 2 vectors in your vector space and you add them up, you'd better get a vector in that vector space. Okay, so if you take 2 things in the thing that we're calling a vector space, you still get something that's in that vector space, okay? And we call this closure, okay? And this is a very common property. You'll see this in modern algebra too if you take that course. You're going to see this property popping up all over the place. All right, so in other words, well, if you just add 2 things of one particular type, you get another thing of that type. The next property is a little bit less trivial. Next property just says it doesn't matter the order in which you add things up. And again, so like when we're going through these properties, keep in the back of your mind Rn as the prototypical example, right? These properties here, they were designed all just to mimic properties of Rn. What people did was they said, okay, like we want to do linear algebra on sets other than just Rn. What important properties does Rn have that lets us do linear algebra? And then they came up with these 10 properties here. These are what let us do linear algebra. So like this first property here, if I add up a list of n numbers with another list of n numbers, yeah, I get another list of n numbers, great. The second property, if I add up 2 vectors in Rn, does it matter the order that I add them up in? No, it doesn't. Okay, so we want that same property to hold in arbitrary vector spaces as well. Okay, and this property is called commutativity. Similarly, if you add up real numbers or real vectors, you can place parentheses however you like. So we want that same property to hold in arbitrary vector spaces, and this property is called associativity. It doesn't matter if you do v plus w and then plus x, or if you do w plus x and then plus v. You get the same thing either way. Okay. All right. The fourth property that we want vector addition to satisfy is we want there to be some vector that does nothing under vector addition. Okay, so there's got to be some vector that we call the 0 vector in the vector space that has the property that whenever I add it to some vector, nothing changes. Okay, so v plus the 0 vector is always just equal to v. Okay. And then the fifth property is we want vectors to have negatives. We want them to have inverses, really. Okay, so no matter which vector v I choose, there is some vector negative v with the property that when I add them up, I get that 0 vector from property d up here. Okay, I get the vector with the property that adding it does nothing. Okay, so we think of like the 0 vector sort of as like the nothing or the null element. So there's got to be some way to get back to that null element by adding some other vector that we call negative v. Okay, and again, like in Rn, all of these properties are very, very natural, right? The 0 vector is just the vector with every entry equal to 0. The vector negative v, well, you just stick a minus sign in each entry of the vector and so on. So again, in Rn, of course you can do these things, but we also want to be able to do these things in arbitrary vector spaces. All right, so those are the properties of vector addition that we need to have. Now let's look at the properties of scalar multiplication, okay? And property F here, the first scalar multiplication property, again, it's very natural. If you take a vector and you multiply it by a scalar, you'd better get a vector. And like in other words, if you take something that's in the vector space and you multiply it by a scalar, you get something still in the vector space, okay? All right. Next properties are also fairly natural, but they sort of pin down how scalar multiplication interacts with vector addition. Okay, so both of these properties here, they're called distributivity, and this first one just says if you do vector addition and then scalar multiplication, well, you can just distribute in the obvious way. You can do scalar multiplication on each of them individually and then add them up. Okay, whereas property H here says if you do addition of scalars and then multiplication by a vector and then scalar multiplication, well, again, you can split that up as 2 scalar multiplications and then addition. So both of these are just called distributivity. And both of these, again, if you think in terms of real numbers or vectors consisting of real numbers, right, Rn, then both of these properties are very natural. Of course you can do these things in Rn. Well, we also want them to hold in arbitrary vector spaces. right? And then I and j down here, these are also, nothing too surprising happens here. I mean, these are just saying multiply by a scalar, then multiply by another scalar. Well, you could multiply the scalars together and then do scalar multiplication instead. Doesn't matter what order you'd use. And similarly, every field, right, every set of scalars, every field, has a number 1 in it. And this bottom property here just says that, well, if you do that number 1 scalar multiplied by a vector, you get that vector. It doesn't change it at all. Okay, so again, we haven't talked about fields at all, but this property is always true. Like if you do like 1 times x, where x is a member of the field, you always get x. That's the definition of 1 in a field. Okay, so it always leaves everything in a field alone. We also want it to leave everything in the vector space alone. Okay, but again, like it's not meant to be surprising. It's just we need it to be true for this to be a vector space. Okay? Basically, without these nice properties, you're not going to be able to prove anything about vector spaces, so you're not going to be able to do anything with them. All right, so let's maybe try to clarify just a couple possible points of confusion about vector spaces before we go forward with some examples. All right, so yeah, this field that we talked about, F, it's just, again, we think of it as a set of numbers, which basically just means it's a place where we can add, subtract, multiply, and divide according to basically the usual laws of arithmetic. Okay, so we're not going to go into the details. We're not going to write down a formal definition of it, but examples include, the set R of real numbers, the set C of complex numbers, the set ZP that we talked about on the previous page of numbers 0 up to p minus 1, as long as p is a prime. Okay, as long as p is a prime number, then this is a field. Okay, for the purposes of this course, we're only going to look at R and C, though. We're going to look at the sets of real and complex numbers. All right, so don't worry about fields too much is the short version there. It's good to be aware that vector spaces are defined over them in general, but for this course, real and complex numbers are enough. All right, and another thing to keep in mind is that vectors and the vector operations that we're going to use, so vector addition, scalar multiplication, they don't need to look anything like vectors that you're used to. So they don't need to look like lists of real numbers, and the operations don't need to look like usual addition, scalar multiplication. As long as they satisfy this laundry list of properties up here, you're good to go. It's a vector space, so you can do linear algebra on it. Okay, so let's do a couple examples. All right. So to start off, let's try to convince ourselves that Rn is a vector space. And it had better be a vector space, right? It's our motivating example of a vector space. It's why that definition that was up above is the way it is. It's where those 10 properties came from. So let's try to convince ourselves that, yeah, they really do hold. Okay, so let's show that this is a vector space. The way that you do that is you just show the 10 properties hold. You check all 10 of them. Okay, so property A, well, let's go back up and remind ourselves. Property A just says, well, if I add 2 things in the set, I get something in the set. Okay, so in other words, if I take a list of n numbers, V, and I take another list of n numbers, W, add them up. Do I get a list of n numbers? Do I get another member of Rn? And yeah, of course you do. Just think about how vector addition is defined in Rn, right? You just add up the entries of those vectors. And look, here, this is another list of n numbers. So yeah, that's in Rn. Okay, so property A, we just say, yeah, check. It's sort of obvious. There's nothing to show there. Okay, property B. Property B is commutativity of vector addition. So V plus W, does that equal W plus V? Well, let's just look at the definition. V plus W is the vector whose entries are V1 plus W1, V2 plus W2, up to Vn plus Wn. Same thing if you add in the other order. W plus V, that's W1 plus V1, W2 plus V2, and so on, up to Wn plus Vn. Okay, but now how do we show that these two are equal? How do we show that these two are equal? Well, just all of these entries here, they're all just real numbers, right? V1 is a real number, W1 is a real number, and we know that real number addition is commutative, okay? So you can just swap the order here. V1 plus W1, yeah, that's W1 plus V1. Similarly, V2 plus W2, yeah, that's W2 plus V2, and so on. So we just use commutativity of real number addition to sort of latch on and get commutativity of vector addition out of that. So yeah, property B holds there. Okay, property C, that's associativity. Okay, so let's go back up and look. Property C is this property here, V plus W plus X equals V plus W plus X. So it doesn't matter how you group parentheses. Right? And this property, you prove it in the exact same way that you prove property B. It's just a little bit uglier because you have 3 vectors instead of just 2 now. But you just leech on to associativity of real number addition in each entry of these vectors. Okay, so again, nothing really surprising here. None of these properties are meant to be hard to show. Okay, it's just going through and sort of doing at least the 1 minute mental check that, yeah, it actually does hold. Okay, it's just convincing yourselves that you actually have checked and verified it. Property D, we need to know that there's a zero vector, a vector with a property that if you add it to anything else, you don't change that anything else. And in this vector space, the zero vector is just the vector with every entry equal to 0. That vector works. If I add that to anything, I'm just adding zeros to each of its entries, so nothing changes. Okay? Property E, well, I need to show that negative vectors exist. In other words, there's some vector, no matter which v I choose, there's some other vector called minus v that I can find that when I add them up, I get the zero vector. And the way to do this is you just stick a minus in front of each entry of v, okay? If I add v to this vector here, then I just get v1 plus minus v1, well, that's 0. And then v2 plus minus v2, that's 0, and so on. You get a 0 in each of the entries, which is the zero vector. It's this guy here, so great. This is how negative vectors are defined. Negative vectors exist, therefore property E is satisfied. All right, and then maybe by this point we're getting the idea that nothing's really surprising with any of these properties. So I'm just going to say that properties F through J, the remaining 5 properties, those are all very similar. Okay, nothing surprising happens with any of these. Property F, we need to show that if you take a vector, a list of n numbers, and you multiply it by a scalar, it's still a list of n numbers. Oh, I mean, of course it is, right? There's kind of nothing to show there, okay? And similarly, the other properties, you just leech off of properties of the set of real numbers, okay? So maybe try those on your own. Again, like you don't have to actually like even write anything out necessarily. It's just convince yourself that they're true. All right, let's go to more interesting examples of vector spaces that aren't the one that we already saw in the previous course. All right, so our first sort of non-trivial example of a vector space is what we're going to call funky curly f there. And what it is, it's the set of all functions that take in a real number and spit out a real number. So the set of all real valued functions. Turns out that's a vector space. So let's convince ourselves of this. Again, how do you do that? Well, you have to show those 10 defining properties of a vector space hold. All right, so let's go through that, at least sort of go through it to convince ourselves of it, even if we don't write down all the details. All right, so property A, we have to show that if we take 2 functions and we add them up, we get a function. Okay, well, before we do that, maybe we should know like what is adding in this case and what is scalar multiplication. Addition just means entry-wise, okay? So if you add 2 functions, well, that just means you do the entry-wise addition of those 2 functions. And similarly, if you do scalar multiplication, it's entry-wise scalar multiplication. All right, so yeah, I mean, if you add up 2 functions entry-wise, you get a real valued function. Moving on, property B, we have to show commutativity. If I do f plus g, if I add up 2 functions, well, I can add them up in the opposite order and I get the same thing. Well, the way to do this is we've got to go to the definition of what vector addition is, okay? So f plus g, the function f plus g applied to some number, what is that? Well, just split it up, we're adding them entry-wise, so this is just the definition of function addition. F plus g of x is f of x plus g of x. All right, and now we're just going to leech off of commutativity of real number addition. F of x is a real number, g of x is a real number, so I can swap those around. F of x plus g of x, that's g of x plus f of x. Okay, and now again, I use the definition of function addition in this vector space. G of x plus f of x, well, that's the function g plus f of x. All right, so what have we shown here? We've shown that f plus g of x equals g plus f of x, no matter what real number x I pick. Okay, so that tells me that f plus g equals g plus x, right? The way that you test equality of 2 functions is you determine whether or not they're equal to each other on all inputs, and that's all that we've done here. We want to show that f plus g equals g plus x. Sorry, f plus g equals g plus f. So I check that f plus g of x always equals g plus f of x. Great. So property B holds. Property C, again, remember this is associativity. I want to show that if I do the sum of 3 functions, but grouping parentheses in different ways, I want to show that if I do like f plus g plus h, that equals f plus g plus h. All right, so how do we do that? Well, again, it's just going to be similar to part B. I'm not going to go through the details, but you just check how f plus g plus h acts on every input x, and similarly for f plus g plus h. Okay, so just group parentheses on the functions differently, and you'll just end up with an f of x plus g of x plus h of x, and then you can regroup using laws of addition for real numbers. Okay, so you can just leech off of the corresponding properties of real numbers. All right, property D says there's got to be a zero vector in this vector space. So the zero vector, well, now we're saying a vector is a member of the vector space. So in this case, the vector, right, every vector is a function, right? It's a member of the set V that we're talking about. All right, so the zero vector in this case, it's the, well, I mean, it's not always obvious what the zero vector is, but in this case, it sort of seems like the most natural choice. It should be the function that just always outputs zero, right? That seems like the most natural candidate for a zero function, right? All right. And it turns out that, yeah, I mean, if you sort of check this, right, this function that just always spits out zero, if I add that to another function, it turns out it doesn't change that other function at all. And that's sort of a trivial calculation, right? You're just adding zero to the output of the other function everywhere. Okay, so it doesn't actually change it at all. So this works. This is our zero vector. It's the zero function. All right, and similarly, negatives, they're sort of defined in the obvious way. Negative f, well, that's the function that just always outputs negative f of x. Right? Nothing too surprising there. Again, just because we're doing things entry-wise, nothing surprising happens with any of these definitions, okay? So properties A through E all hold, and then again, properties F through J, try them on your own, nothing surprising with them. If you take a function and multiply it by a scalar, yeah, it's still a function, and so on, okay? So all those properties, they hold as well. All right, so yeah, so that's our first example of, sort of our first non-trivial example of a vector space, is that funky, the set of real valued functions. So we're gonna be able to do linear algebra on it. All right, another sort of not immediately obvious example is the set of matrices. So when I use this funky script M here with subscripts, this means the set of M by N matrices. And then this means that the entries of those matrices come from the field F, okay? So they could be real numbers, could be complex numbers, whatever. It doesn't matter as long as their entries come from some field. All right, so the M by N matrices, it turns out that is a vector space as well. So we can do linear algebra where we think of matrices not as acting on vectors, but as the vectors themselves. So that's kind of neat, and we'll see a bunch of useful applications of that idea. All right, so how do we convince ourselves that this is a vector space? Again, you go back to the definition. You have those 10 properties that you got to check. All right, so, and it turns out that all of these properties, proving them is going to be almost identical to how we prove them for Rn itself. And the reason for that is, like, if you think about it, matrices, in a sense, they're just lists of numbers. It's just that list of numbers is arranged in a 2D array, but it's just a bunch of numbers listed out. Okay, just like Rn. So, I mean, proving all of these properties that show that this is a vector space, it's almost identical to how we proved it for Rn. For example, property A, I gotta show that if I take two matrices and add them up, I get a matrix. Trivial, of course you do. Property B, if I take two matrices and I add them up, do I get the same thing no matter which order I add them up in? Is A plus B always the same as B plus A? Yeah, of course it is, right? You're just adding real numbers up a whole bunch of times in each entry of that matrix. And you can swap the order in each entry because those are just real numbers or complex numbers or whatever numbers coming from some field. Okay, so property B holds. Property C, associativity. You can swap orders of parentheses in each entry of the matrix addition, so you can swap order of parentheses in the entire thing, and so on, okay? It's going to satisfy all 10 of those properties. We're not going to go through them explicitly because, well, it's boring, okay? We're going to do, hopefully, more interesting things soon. All right, let's instead go through a less trivial example, one that's actually kind of really weird and highlights this fact that the vector operations don't need to look anything like you're used to addition and scalar multiplication looking like, okay? They can look however ugly and however weird they like as long as they satisfy those 10 properties. All right, so what's this example here? So V, our vector space this time, it's going to be the set of positive real numbers, so strictly positive real numbers, not including zero. Okay, but if you consider this set with the usual addition and multiplication operations, it is not a vector space, right? Because if you multiply by the scalar -3, for example, you're going to take positive numbers out of that set. So it won't be closed under scalar multiplication if you do addition and scalar multiplication in the usual way. But instead, if you define addition and scalar multiplication in a weird way, then it turns it into a vector space. So if you define vector addition as usual multiplication, and if you define scalar multiplication as usual exponentiation, then it turns out that this is a vector space, okay? And this sort of highlights an important point. A vector space is not just a set of objects. A vector space, it's a set of objects together with two operations. Those two operations, addition and scalar multiplication, are part of the vector space. If you change them, it might turn it into a different vector space, or it might turn it into not a vector space, okay? Like, it depends on what those operations are. A lot of the time we just take them for granted. For example, if we're working with matrices, I mean, we just assume that addition is usual addition and scalar multiplication is usual scalar multiplication. But we can define them in weirder, different ways if we want to, okay? They are package deals with the vectors in that set. Okay, so let's go through this example. Let's show that these weird operations, these weird additions and scalar multiplications, turn this set here into a vector space, all right? So again, you do it the same way you always do, okay? You look at those 10 defining properties of a vector space and check if they hold, okay? And just as a sort of a brief note on notation here, because we have sort of two different types of multiplication going on here, and because these operations are defined in such a weird way, I'm using different notation for vector addition and scalar multiplication than usual. Vector addition, I'm denoting by this weird plus in a circle, and scalar multiplication, I'm denoting by this weird dot in a circle, whereas usual sort of non-vector space operations, I'm denoting in the usual way. So here when I write x times y, I mean just the numbers x times y. I'm not thinking of them as vectors there. And x to the power c, I just mean usual, like number x to the power number c. I'm not thinking of them as vectors or anything like that, okay? Just to try to disambiguate, like when I do c times x, like do I mean scalar c times scalar x, or do I mean like this weird operation down here? Okay, anyway, so let's go through those 10 properties here. So I have to show that if I do vector addition of two vectors in that set, I get something in that set. I've got to show that it's closed under vector addition. Okay, so I've got to show that x weird o plus y is still in that set. Okay, well, how's that vector operation defined? Vector addition of x and y, that's the numbers x times y, okay? So the vector addition is x times y, and then remember that if x and y were both in that set, so x has got to be bigger than 0 and y's got to be bigger than 0. So I'm multiplying together two numbers that are bigger than 0. So it's still bigger than 0. So it's still in that set, right? If you take two numbers that are positive, you multiply them together, still positive. So it's still going to stay in this set. This set is closed under multiplication, which is vector addition. Okay, so that's great. That's what I want. That's property A here. Property B, I've got to show that vector addition is commutative. I've got to show that if I do vector addition of x and y, I get the same thing as if I do vector addition of y and x. Okay, and again, this follows straightforwardly from properties of real numbers because vector addition is real number multiplication. X plus y, well, that's x times y. All right, so x vector plus y is just x times y, which real number multiplication is commutative, so that's y times x, which is y vector plus x. Okay, so yeah, x vector addition y is the same as y vector addition x. All right, and property C, yet again, I'm going to gloss over property C here. This is that associativity property. You just do the same thing that we did in property B, except with three vectors, right? We have to show that x vector addition y plus z is the same as x vector addition y vector addition z, okay? It doesn't matter how you group parentheses there. But again, it just follows from the fact that you can group parentheses in real number multiplication however you like. All right, property D is where things start to get really weird. And again, it's just because these vector operations are defined so weirdly. The zero vector, think about what the zero vector needs to be in the vector space. It needs to be something that when I do vector addition with it, it doesn't change the other vector. Okay, but vector addition in this set is just normal real number multiplication. So I need a vector such that I need to find some positive number such that when I multiply by it, I don't change the other number. Well, that's the number 1, not 0. Like, it's really tempting to say, oh, the zero vector in this set of numbers is the number 0, but it's not. The number 0 is not even in this set, right? This set V here does not have the number 0, but it does have the number 1. And it turns out that 1 is the zero vector, right? The zero vector is the number 1 because the vector addition of 0 with any other vector is that, well, that would equal 1 times that other number x, which is just x, which is great. That's what we wanted. Vector addition with 0 didn't do anything. All right, so that's where things start getting weird. And again, it's just because we've defined these operations in such a weird way. All right, and then property E is also kind of weird just because property D was weird, right? Property E sort of leeches off of property D. Property E, we need to find a negative vector, okay? And what's a negative vector gotta be? Well, it's got to have the property that if I do x plus minus x, I get the 0 vector. In other words, x vector addition minus x has got to give me the number 1. All right, so it turns out that the way that you've got to find negatives is as reciprocals, right? Okay, so let's go through this. Why does this work? If I do x vector addition minus x, what do I get? Well, vector addition is just real number multiplication. So x plus minus x is x times 1 over x. Okay, multiply those together, great. I get the number 1, which is the 0 vector. So that all works out. If I take a number and add it to its negative, I get the 0 vector, which is what I wanted. That's what a negative needs to do. So yeah, negatives exist. And also this 1 over x, as long as x is positive, 1 over x is also positive. So it's also in the set. So I can do this. All right, property F, now we're getting into the properties of scalar multiplication. And remember, scalar multiplication, that's exponentiation. Okay, so I need to show that if I take the vector x and I scalar multiply it by some number, I'm still in the vector space. Well, how does this work? Remember, scalar multiplication is exponentiation. So I get x to the power c. And as long as x is positive, which it must be because it's from v, then x to the power c will also be positive. So it's also in v. So great, that all works out. Okay, because any exponent, any power of a positive real number is still a positive real number. All right, and then the next few properties are just showing sort of the natural properties of exponentiation, of scalar multiplication here. Okay, so for example, property G, we want this distributivity property to hold. If I do vector addition and then scalar multiplication, I want to be able to split that up. So how does it work? Just go back to the definition of these two operations. Vector addition here, well, that's just real number multiplication. So that's the first step that we did there. And then next up, we got to do scalar multiplication. We got to do the scalar multiplication here, and that's just exponentiation. So C scalar multiple x vector addition y. All that means is x times y to the power c. But now we're just working with a real number. X times y to the power c, that's just x to the power c times y to the power c. And now you can sort of break it up in the other way. This is a number, x to the power c, y to the power c, and they're being multiplied together. Well, that's vector addition. Okay, and similarly, x to the power c, well, that's a scalar multiplication. Y to the power c, that's a scalar multiplication. And then if you look at these far left and right-hand sides, scalar multiplication and then vector addition, and then scalar multiplication, that's exactly what we wanted. That's exactly what distributivity property G is. Okay, so it's kind of weird because we're using properties of multiplication and exponentiation to prove properties about scalar multiplication and vector addition, but it all works out exactly how we would expect it to. Property H is just a different distributivity property. Maybe we won't go through it, but you can check it there. And similarly to properties I and J, nothing weird happens with them. So maybe we've done enough on that vector space now. Okay, so yeah, that vector space has all 10 of those properties. So we can do all of our linear algebra things on it and nothing weird happens. Well, I mean, a little bit of weird stuff happens, I guess, but sort of everything still works out. We can do all of our linear algebra stuff on it. All right, so that's maybe enough for the first lecture. I will see you all for lecture 1.5 shortly, which will be just a sort of a brief introduction to complex numbers.